Okay, let's have a look at question 4. A sample of olive oil with a wick in a jar is ignited and used to heat a beaker containing 500 grams of water. So the amount of water used is given, the mass of water, which is 500 grams. The relevant data for the experiment is included in the table below. So this is a very similar setup to the one that we've seen in question 2 and 3. The initial temperature of water is given, so 21 degrees Celsius. You actually given the heat of combustion of olive oil, so you're definitely not going to have to find it. It's given to you here per grams. You're given the amount of olive oil that was used and the total energy that was lost to the environment. Okay, so what might I ask? Calculate the final temperature of the water. Okay, very interesting. So the question here is asking for final temperature of H2O. So this is now the unknown. We are given the initial temperature of water. Oh, what did I do? Yeah, something is happening to my... Oh, that's fine now. Except I can't spell. Initial temperature of H2O is 21 degrees Celsius. So in order to find final temperature, if you're given initial, essentially what it means is that you need to determine delta T of H2O. In order to find delta T, you probably need to find energy. So you need to find the energy absorbed by the water, and then you can use MC delta T from there. Now, you also given the heat of combustion of olive oil. So we will talk about the fuel. The heat of combustion is 41 kilojoules per gram. And the mass of the fuel that was used was 2.97 grams. And then interestingly, you also told that 28 kilojoules of energy was lost to the environment. So energy loss is 20, oh my god, I really can't remember anything, 28 kilojoules of energy. All right, so the first thing I'm going to do for this question is I'm going to find the actual amount of energy released from the combustion of olive oil. And I can do that by just using the heat of combustion and the mass. So basically, we're working out the energy release when we're burning 2.97 grams of the fuel. And we know that 41 kilojoules of energy is supposed to be released if you burn a gram of the fuel. So the energy release is just going to be just basically 2.97 times 41, which is, so 2.97 times 41, 121.77 kilojoules. So this is the amount of energy that was actually released by the fuel. However, we know from the question that 28 kilojoules of this was lost to the surrounding. So if that is the case, then the amount of energy that was actually absorbed by the water must be 100, well, the difference between the two basically. So the energy absorbed by water must be energy released minus energy loss to the surrounding. So 121.77 minus 28. Okay, minus 28. So we have 93.77 kilojoules. And this is the amount of energy that was actually absorbed by the water. And then from here, you should be able to work out the change in temperature, delta T, because E equal to MC delta T. Delta T must be E over M times C. Now, before we make a colossal mistake, I just want to point out that C is specific heat capacity of water, and it is 4.18 joules per grams per Celsius degree. So if you want to use this value, you need to convert energy to joules. So because I'm extremely lazy, I'm just going to write 93 times 10 to the 3 joules. So make sure you make this conversion, otherwise you're going to have a very small number that would be wrong. So 93.77 times 10 to the 3, the mass of water was given to you to be 500 grams in the question. So we're going to use that. And we're going to use 4.18 joules. Okay, so times 1000 divided by 500 and then divided by 4.18. So I get a change in temperature of 44.9 degrees Celsius. And then you need to find the final temperature. So a lot of students probably stop here and then lose that mark, which is so sad. So final temperature is going to be initial temperature plus the increase. I'm actually gonna go with two significant figures for the final answer, given how the initial temperature was 2 sig fig. So to 2 significant, it is 65.9 if you're going to 3 sig fig, but the final answer should be 66 degrees Celsius. Okay, fun fact, this was actually a multiple choice question in one of the exams, so a fair amount of calculation for one multiple choice question. That's part A. What is part B? Calculate the percentage efficiency of the setup. So percentage efficiency should be fairly easy now because you've gotten everything. Two ways to do it. You can just calculate the percentage loss and then 100% minus that, or we can go straight to percentage efficiency. We don't need to find the heat of combustion, so I'm just going to go E absorb over E release essentially times 100. So there's a few ways to calculate percentage efficiency, but the idea is the same. You just need to get a value from the experiment over the equivalent values that you would get theoretically speaking. Okay, so the energy absorbed was 93.77. I think I have like short-term memory loss and I can't actually remember a number. And what was the other one? 121 point something. I'm just gonna get it from my calculator. 7 seconds. You know, I'm not even gonna justify why I can't remember that number, but I can't. Okay, it looks like everything is actually already correct. This is already the exact value. So 93.77 divided by 121.77 times 100. So I get 77% as the percentage efficiency. Okay, so that is question 4.